This video starts with a counterintuitive daily phenomenon: why regular edible salt never gets moldy no matter how long it is stored. Combining archaeological records of ancient Egyptian mummies and official rituals of salt curing, dating back to China's Zhou Dynasty, we thoroughly break down the biological principle of osmotic pressure that kills microorganisms. We uncover the full 40-day natron salt dehydration process used to craft Egyptian mummies, explain the real purpose behind the shelf life printed on salt packaging, and clear up misconceptions about expired iodized salt. We also introduce the extreme hazards of elemental sodium and chlorine that form salt, alongside the chemical reaction that creates stable sodium chloride. Packed with real-world cases of salt preservation across global civilizations for thousands of years. Extra lesser-known facts including seawater preservation logic, industrial food applications of salt curing, causes of salt caking, and osmotic pressure tolerance limits of microbes. This video fully unpacks the complete knowledge system behind ordinary table salt, spanning biology, chemistry, and human history, with easy-to-follow explanations and solid hardcore facts. Hashtags, fun science facts, salt science, mummy mystery, osmosis explained, everyday science chemistry facts, ancient preservation tech daily knowledge full English translation of the main script. Edible salt that we use every single day in the kitchen can sit for 10 or even 20 years without developing a single spot of mold. Even in hot and humid storage conditions, flour gets moldy, rice spoils, and white sugar clumps up with harmful bacteria growing inside it. Only salt stays perfectly clean with zero risk of deterioration. Behind this simple observation lies an ancient biological law that has existed for thousands of years. In fact, the core principle the ancient Egyptians used to preserve pharaoh mummies over 3,000 years ago is exactly identical to the plain table salt sitting in your kitchen cabinet. Most people first learn that salt resists mold from learning about Egyptian mummies. Many viewers ask why royal mummies buried underground for millennia remain intact with clear body contours instead of rotting away. The answer has nothing to do with mysterious witchcraft or magic. Egyptian craftsmen mastered the powerful dehydration ability of salt compounds. The key step of mummification involved placing the fully prepared human body into piles of natural natron salt for 40 full days of resting. Many wonder what the difference is between natron and regular household table salt. In truth, both are high concentration alkaline salts that share nearly identical water-absorbing osmotic pressure properties. During those 40 days, salt continuously and thoroughly draws out all free moisture from every part of the body: muscle fibers, internal soft organs, and tiny gaps in the skin. Every drop of water microbes need to survive is completely removed, fundamentally cutting off all essential conditions for bacteria and mold to reproduce and live. At this point, it becomes clear that stripped of mythical legends, a mummy is simply agent piece of meat, preserved through extreme salt dehydration, working on the exact same logic as the cured bacon and salt-cured ham we make locally. As long as the high-salt environment inside the body remains stable long-term, damp underground conditions and the erosion of time can barely cause damage. Time struggles to break down fully dehydrated, high-salt matter, which explains why numerous unearthed royal Egyptian mummies still retain sharp outlines after more than 4,000 years. The oldest prehistoric mummy discovered by archaeologists dates back 4,200 years, proving that humans perfected salt-based dehydration preservation as early as prehistoric civilizations. To fully understand why salt prevents mold and rot, we must first clarify the fundamental mechanism of mold growth. Food spoilage never happens spontaneously within ingredients themselves. It is simply a process where mold, bacteria, and other environmental microorganisms attach to food to feed and multiply rapidly. Microbes require three non-negotiable conditions to live and multiply: suitable temperature, sufficient nutrients, and most critically, available free water. Water acts as the core medium for cellular operation and metabolism for microorganisms. Without water, even abundant nutrients cannot support cell division and proliferation. Salt perfectly targets this fatal weakness of microbes. Mold and harmful pathogens cannot survive in high-salt environments. Even if bacterial or mold spores land on salt surface by chance, salt immediately launches a microscopic osmotic pressure attack, a universal cellular rule across all biological life forms. We will explain these microscopic changes in plain language. Roughly 70% of all bacterial cells consist of water, and intracellular fluid maintains a fixed osmotic pressure value. When exposed to highly concentrated sodium chloride salt, a massive osmotic pressure gap forms between the inside and outside of bacterial cells. Acting like a greedy, microscopic water predator, salt uses strong osmotic potential to forcibly extract water nonstop from inside bacterial cells. This is not just surface drying, but a standard biological process known as plasmolysis. The cell membrane detaches entirely from the cell wall. Cytoplasm shrinks severely due to water loss, and internal organelles and active substances quickly become inactive. Microbes can do nothing as their cells are drained dry, eventually turning into lifeless microbial husks. This elimination mechanism is efficient and definitive with no room for survival, making high-salt environments an absolute dead zone for microorganisms. Humans have relied on this osmotic pressure, sterilization, and preservation method for thousands of years. Before refrigerators became widely available worldwide, salting fresh meat and seafood with plenty of salt was the most mainstream and reliable preservation method across all civilizations. People artificially created zones completely uninhabitable for microbes. With sufficient salt concentration to suppress all common pathogenic bacteria via stable osmotic pressure, meat could be stored at room temperature for months or even years without spoiling. Assyrian, as the Shang and Zhou dynasties in Chinese civilization, salt curing for food preservation was formalized into official ritual systems. The Zhou Dynasty established a dedicated official position called the Laren, whose sole duty was producing salt-cured dried meat for royal banquets and sacrificial ceremonies. Strips of large livestock preserved with salt and air-dried were called fu, while whole small poultry cured and dried were known as la, forming a complete early system of salt-preserved meat craftsmanship. Even today, Jiangnan cured ham, Cantonese preserved waxed meats, Sichuan salted pork, and thousand-year-old salted fish curing techniques along coastal regions all follow this ancient osmotic pressure principle. Across the globe, common citizens in ancient Rome and ancient Greece also preserved meat with salt. Salt-cured meat was standard provisions for long-distance land trade in the Middle Ages and long ocean voyages during the Age of Discovery. This proves salt's preservation value is shared survival wisdom discovered by all humankind, rather than an invention exclusive to a single civilization. At this stage, many viewers raise a big question. If pure salt never goes bad or develops mold, why does every package of commercial edible salt clearly print a shelf life? Is this label completely unnecessary? The answer is definitely no. The shelf life marked on salt packaging never applies to sodium chloride itself, and serves two key purposes. The first consideration relates to the plastic packaging holding the salt. While sodium chloride is chemically stable permanently, its plastic packaging gradually ages over time. Most table salt sold commercially is sealed in food-grade polyethylene plastic bags. Per national food safety standards, legally compliant food plastic packaging has strict upper limits for plasticizer and microplastic migration when manufactured. However, plastic has a natural aging cycle. After years of light exposure, temperature fluctuation, and slow oxidation, the polymer structure of plastic degrades gradually. Additives, trace plasticizers, and microplastics produced by plastic breakdown may slowly migrate into the salt. Extended storage far past the printed expiry date accelerates packaging aging and slightly raises the risk of contaminant leaching. This is the primary reason manufacturers add shelf life labels. Many people worry that ordinary salt bags will quickly exceed safe plasticizer limits during storage. We can clarify this with current national standards. China's active standard GB 4806. 7/2023 for food contact plastic product sets, strict maximum migration limits for plasticizers. Salt packaging from reputable major manufacturers keeps hazardous substance migration far below safety threshold, within the official shelf life under normal storage, so there is no need for unnecessary panic. Still, manufacturers must inform consumers of potential long-term aging risks, which forms the first purpose of shelf life labeling. The second key element tied to shelf life is artificially added iodine in salt, the essential nutritional component in household iodized salt. While sodium chloride remains stable for centuries, iodine is highly chemically reactive and unstable by nature, prone to volatilization and loss from sunlight, high heat, and humid air. We can distinguish two common iodine additives. Potassium iodide, used in older salt formulas, has stronger volatility, while modern mainstream salt uses more stable potassium iodate to greatly slow iodine loss, though permanent retention remains impossible. Industry test data shows that regular refined iodized salt stored away from light and moisture sees obvious iodine content decline after roughly 3 years of storage. When the 5-year printed shelf life ends, the sodium chloride structure and saltiness of the salt remain fully unchanged, yet most added iodine has evaporated away. The salt simply transforms from functional iodized salt into regular non-iodized refined salt. The salt itself has not spoiled. It only loses its supplementary nutritional benefit ophiodine intake and remains safe for cooking consumption. This is the core reason national authorities mandate shelf life labeling for iodized salt. We add official regulatory knowledge here. According to China's former food label management regulations, pure raw sodium chloride salt and non-iodized salt are exempt from mandatory shelf life labeling, categorized alongside vinegar and solid white sugar as products safe for long-term room temperature storage with proper sealing. As public food safety awareness rises, major salt manufacturers voluntarily add shelf life dates to iodized salt, low-sodium salt, selenium-fortified compound nutritional salts. Refined iodized salt commonly carries a 5-year shelf life, while low-sodium blended nutritional salts usually have a 3-year expiry date. These dates only remind consumers to consume the salt, while iodine content remains intact to maximize nutritional benefits, not to claim expired salt produces toxins or spoils completely. Everyone must correct this critical misunderstanding. Never throw away expired iodized salt blindly. Expired iodized salt merely lacks iodine and is perfectly safe for regular cooking use. Once we understand the logic behind salt shelf life, we can dive deeper into salt's chemical composition, which will surprise most readers. The two basic elements that make everyday table salt are highly dangerous reactive chemical substances on their own. Yet when combined via chemical reaction, they completely lose their violent traits to form extremely stable sodium chloride, common table salt. First, sodium. Elemental metallic sodium is an extremely reactive alkali metal. Dropping a small chunk of pure sodium directly into water triggers an intense violent chemical reaction, releasing massive heat and flammable hydrogen, gas alongside vigorous combustion, and even minor explosions. A sufficient amount of metallic sodium can shatter water containers with ease. Due to its obvious danger, laboratory metallic sodium must be fully sealed and submerged in kerosene to isolate air. Even minor contact with water vapor causes dangerous incidents, classifying it as a strictly controlled high-risk chemical in chemistry labs. The second component is chlorine. Elemental chlorine gas is a notorious lethal toxic chemical weapon used in early warfare. Chlorine carries strong irritation and corrosiveness. Inhalation of small volumes of high-concentration chlorine burns respiratory tract mucous membranes, while heavy inhalation causes severe permanent respiratory damage to humans, alongside severe toxicity to all plants and animals. Strict safety protocols govern chlorine transportation and industrial usage at all times to prevent accidental exposure. These two violently reactive, hazardous elements undergo a fierce redox reaction when metallic sodium ignites in a chlorine atmosphere. Sodium atoms lose their outermost electron, which chlorine atoms capture to form stable sodium cations and chloride anions locked firmly together by ionic bonds. After this chemical combination, all dangerous properties of the two elemental substances vanish entirely. Positive and negative ions arrange neatly into a cubic crystal lattice, creating chemically inert sodium chloride crystals. The main component of edible salt. Under normal room conditions, sodium chloride resists decomposition and rarely reacts with air or plain water, explaining its exceptional long-term stability and resistance to spoilage, rooted in this robust ionic crystal structure. Many viewers ask why electrolyzing salt water can separate chlorine gas and sodium hydroxide again if sodium chloride bonds are so stable. The difference lies entirely in reaction conditions. The natural ionic structure of sodium chloride is extremely stable, and only extreme conditions such as high current electrolysis or ultra-high pressure can forcibly break ionic bonds to split the constituent elements. Standard home cooking and room temperature storage environments and never initiate such separation reactions, so there is zero risk of consuming elemental sodium or chlorine through heating salt. The two dangerous elements are securely bonded into safe, stable table salt fit for daily consumption. We will expand on the osmotic pressure principle with real-life daily scenarios to help you fully grasp salt sterilization mechanism thoroughly. When treating wounds medically, we use 0.9% normal saline solution, a concentration carefully calibrated to match the osmotic pressure of human blood cells exactly. Water flows evenly in and out of cells, without causing swelling from excess water intake or shrinkage from dehydration, making saline safe for wound cleaning and intravenous fluid replenishment. By contrast, flushing an open wound with highly concentrated strong brine creates a sharp stinging sensation, caused by mild plasmolysis of human skin cells under high salt osmotic pressure. the exact same process that dehydrates and kills bacteria, confirming the real effect of osmotic pressure. Furthermore, pickling vegetables and preserved duck eggs atone forces water out of produce and egg yolks under high-salt osmotic pressure, resulting in firm, oily egg yolks and well-seasoned pickled vegetables. Centuries of traditional household pickling techniques unconsciously apply this scientific osmotic pressure principle. High sugar environments such as concentrated syrup and honey also deliver preservation effects through identical high osmotic pressure that strips microbes of water. Yet sugar has a far lower maximum osmotic pressure capacity than salt, resulting in much weaker preservation performance. This explains why cured bacon and salted fish require heavy salting for long-term storage, while sweet preserved confectionery only keeps for a short period and easily turns moldy with moisture exposure. Returning to natron dehydration for Egyptian mummification, many wonder how natron differs from regular table salt. Natural natron used for mummy production originated from the Natron Dry River Valley in the Nile Delta region, primarily composed of sodium carbonate, sodium bicarbonate mixed with sodium chloride. This composite alkaline salt delivers stronger dehydration power than pure table salt, while also neutralizing acidic substances released during bodily decomposition to suppress saprophytic bacterial growth. Full mummification for royal pharaohs took up to 70 days. The first 40 days focused on complete dehydration with natron salt, followed by cavity filling with aromatic spices, resin sealing, and layers of linen, wrapping with multiple overlapping preservation methods. Common civilians received simplified mummification via soaking in salt alkaline solutions before air drying. While the process was basic, its core mechanism remained salt-based dehydration, identical to curing meat. Multiple archaeological experiments have recreated the ancient 40-day natron salting process with modern technology, perfectly replicating preservation techniques from thousands of years ago, proving the scientific validity of salt dehydration preservation, validated over millennia, rather than mere folklore. After covering preservation principles, we answer frequent daily questions about purchasing and storing salt. Many households stock up on multiple packs of salt to store for years at a time. Based on our earlier analysis, pure non-iodized salt remains safe to consume for over a decade with proper airtight moisture-proof sealing with no risk of spoilage. Iodized salt is best consumed within 3 years to retain full iodine nutrition, while minimizing minor long-term packaging aging risks. The ideal storage containers for salt-air-sealed ceramic jars or glass canisters. Avoid prolonged storage in open plastic bottles, and keep salt in cool shaded areas away from high heat near kitchen stoves. This prevents moisture absorption and clumping while slowing iodine volatilization to preserve salt quality optimally. Low-sodium potassium-enriched salt, selenium-fortified blended nutritional salts, and other compound-enhanced salts commonly carry 3-year shelf lives. Beyond iodine, added mineral trace elements slowly deplete over time, so expiry dates target the activity cycle of blended additives only. Sodium chloride itself remains permanently stable. Always distinguish between the limited lifespan of nutritional additives and permanent stability of the salt base itself, and abandon the false belief that expired salt cannot be eaten. We further interpret sodium chloride's permanent stability from a chemical bonding perspective. The ionic bond energy of sodium chloride is extremely strong. Under normal temperature and pressure, sunlight, ambient temperature, atmospheric oxygen, and carbon dioxide cannot damage its crystal structure. Sodium chloride will not oxidize, hydrolyze, or sustain microbial growth. Mold requires carbohydrates, protein, and organic matter as nutrition to grow, yet salt consists solely of inorganic positive and negative ions with zero organic nutrients mold can feed on. Even if mold spores land on salt grains, they face both a complete lack of food sources and immediate dehydration from high osmotic pressure, leaving zero chance of survival or reproduction. This is the ultimate reason table salt never develops mold. In sharp contrast, flour, rice, sugar, and dried staple goods are rich in organic starch and protein, ideal food sources for microbes that trigger rapid mold growth once humidity levels rise. One fascinating extended fact: extremely high salinity in deep-sea basins and salt lakes makes survival impossible for common aquatic bacteria, with only a tiny number of specialized halophilic microbes capable of tolerating extreme osmotic pressure. These rare species never appear in regular household environments, confirming why domestic table salt never molds. After learning how elemental sodium and chlorine combinato form salt, many viewers question the underlying periodictable rule behind this reaction. Group 1 alkali metals on the periodic table: naturally form ionic bonds easily with group 7 halogen nonmetals to create stable ionic compounds. Sodium is a classic alkali metal, while chlorine is a standard halogen element, making their chemical combination an inevitable result of elemental properties. The violent behavior of pure elemental forms stems from unstable outer electron configurations. Once outer electron shells reach full stable saturation, substances become chemically calm and inert, comparable to two short-tempered people becoming steady and balanced once paired with complementary personalities. Sodium chloride formation stands as the textbook example of this rule. The modern industrial chlor-alkali industry centers on electrolyzing concentrated salt water to reverse the chemical bond, separating chlorine gas, sodium hydroxide, and hydrogen gas for mass chemical formaturing. This industrial splitting process consumes massive electric energy, completely unachievable under regular household conditions, so consuming table salt possesses no threat of exposure to toxic elemental substances whatsoever. We continue tracing thousands of years of human salt usage history. The development of salt extraction and application perfectly mirrors the evolution of human food preservation technology. Neolithic Chinese ancestors mastered mining and refining sea salt, well salt, and lake salt early on. Today's domestic salt production structure consists of 87% well and rock salt, 10% sea salt, and 3% lake salt. Abundant salt supply allowed salt curing preservation techniques to spread nationwide. In cold northern winters without fresh vegetables, families pickled Chinese cabbage and salted vegetables for long-term consumption. Water-rich southern regions perfected thousand-year-old salted fish preservation methods, while southwest China's oil-preserved salt-cured pork can remain edible for years sealed with oil, all relying entirely on salt's osmotic preservation power. Before refrigerators existed, salt served as nature's permanent household refrigerator. The ancient Egyptians simply upgraded salt dehydration technology to preserve human remains from mummification, representing cross-industry application of the exact same physical scientific principle. Even within the modern food processing industry, high salt curing remains a mainstream preservation technique, paired with modern low-temperature refrigeration and vacuum packaging for dual food storage protection. Beyond food preservation, osmotic pressure sterilization principles extend to medical hypertonic saline for swelling reduction, industrial seawater desalination, water treatment sterilization, and countless other fields. This tiny kitchen staple applies fundamental physical and chemical science to every aspect of human daily life. We can now form a complete logical conclusion to wrap up all key points. First, table salt resists mold permanently because sodium chloride contains no organic nutrients for microbes, while high-concentration salt uses osmotic pressure to strip water from bacterial and mold cells to trigger fatal plasmolysis, eliminating microbial reproduction by cutting off both nutrition and water supply entirely. Second, 40-day natron salt dehydration for Egyptian mummification and thousands of years of Chinese wax meat curing represent classic real-world applications of this identical osmotic pressure principle, reaching the scientific conclusion across distinct ancient civilizations. Third, shelf life labels printed on salt packaging never apply to sodium chloride itself. They serve two purposes: managing risks of plasticizer and microplastic migration as plastic packaging ages over long storage periods, and addressing volatile iodine content in iodized salt. Depleted iodine only removes the salt's iodine supplementation function without causing spoilage or toxin formation in the salt itself. Finally, salt is formed from chemically dangerous elemental sodium and chlorine locked together by robust ionic bonds into stable sodium chloride. These two hazardous elements transform into safe, mild table salt once bonded chemically, creating the everyday seasoning essential to our 3 daily meals. Many people find their household salt absorbs moisture and clumps together, commonly mistaking this physical state for spoilage. In reality, salt clumping is a completely normal physical occurrence unrelated to mold or deterioration in any way. Sodium chloride naturally holds strong hygroscopicity, meaning powerful water absorption capacity. During humid rainy seasons or southern China's returning damp weather, salt grains rapidly capture airborne moisture to stick together into hard lumps. Even solid clumped salt remains pure sodium chloride once crushed, retaining full seasoning flavor and antibacterial preservation functionality fully intact. Never discard clumped salt unnecessarily, which only wastes food for no reason. Higher purity refined salt actually experiences less frequent clumping, while unrefined crude sea salt with more impurities absorbs moisture and clumps far more easily. a benefit of upgraded modern salt purification technology most people never notice. Another widely confusing question is why seawater neverates or breeds massive amounts of mold and bacteria, once again explained fully by salt osmotic pressure. The global ocean maintains an average salinity of 3.5%, a concentration sufficient to suppress survival and reproduction of most terrestrial and freshwater pathogenic bacteria. This explains why fresh seafood spoils rapidly once removed from seawater, while seawater itself stays relatively clean and mold-free year-round. We correct a common misconception here. Seawater is not sterile, yet ordinary spoilage bacteria not survive, leaving only specialized halophilic bacteria adapted to high-salt environments. These unique microbes do not cause food rot or seawater mold growth, following the exact same logic that keeps household tables salt mold-free. Coastal ancient populations took advantage of seawater's natural preservation trait to soak and sun-dry seafood locally into long-lasting salted fish and dried seafood goods, achieving food preservation with zero extra salt input, a natural preservation gift from nature. We examine modern food industry's advanced application of salt preservation principles. Walking supermarket snackazels, nearly all long-lasting, ready-to-eat cooked deli meats and air-dried jerky list salt in their ingredient lists. Beyond flavor enhancement, salt's core role is antibacterial preservation to extend shelf life significantly. Many vacuum-sealed cooked foods remove oxygen to block aerobic bacteria growth, yet still require substantial added salt, as vacuum packaging cannot fully inhibit mold and anaerobic bacteria. High salt osmotic pressure suppresses all microorganisms comprehensively, enabling room temperature storage for several months with dual protective measures. Public data released by the China Food Industry Association confirms standardized high salt curing can extend room temperature food preservation cycles by over 6 times. Among all natural preservative-free food preservation solutions, salt curing delivers the highest cost efficiency, widest application scope, and top safety rating without equal. This explains why traditional, preservative-free cured bacon and salted vegetables rely purely on high salt processing for long-term storage, remaining classy household preservation methods after thousands of years. Viewers also wonder why sugar water, rainwater, and mineral water easily turn moldy while salt water does not, rooted entirely in differing osmotic pressure tolerance thresholds. Microbial cells have a fixed upper limit for osmotic pressure resistance. Regular sugar solutions and fresh water carry far lower osmotic pressure than intracellular microbial fluid, allowing bacteria to absorb water freely for survival and nutrient intake. High concentration saltwater osmotic pressure exceeds the tolerance limit of all common microbes, forming an uncrossable survival boundary for all bacterial colonies. Additionally, salt's inorganic chemical makeup cannot be broken down biologically by microorganisms. Mold and bacteria only produce enzymes capable of decomposing organic starches, proteins, and sugars, lacking any biological mechanism to digest sodium chloride. Simply put, salt acts as both a lethal high-pressure environment that instantly kills microbes and a completely indigestible substance offering zero nutrition. With no food to consume and no possibility of staying alive, salt never undergoes mold growth, spoilage, or decay. Finally, we correct a prevalent online science myth. The claim that salt never expires and can be eaten indefinitely requires precise revision. Pure sodium chloride remains permanently stable and mold-proof, yet everyday commercial edible salt consists of processed formulated variants including iodized salt, low-sodium salt, and fortified nutritional blends. Long-term storage does not produce toxins or mold growth in these salts, yet their added nutritional value gradually diminishes over time. Furthermore, salt stored uncovered continuously absorbs airborne moisture, dust, and faint foreign odors. While still safe to eat, cleanliness and flavor quality will degrade slightly. Therefore, the most scientific storage practice involves purchasing salt in small batches regularly, with airtight shaded storage to retain maximum edible value while eliminating minor potential risks entirely. The most practical daily salt usage method for ordinary families. After watching this video, you will never underestimate the humble bag of table salt in your kitchen again. This ordinary household staple encapsulates fundamental hard truths across biology, chemistry, and human natural law. If you enjoy practical, hardcore, everyday science content, hit like and subscribe for more eye-opening, lesser-known knowledge releases.